Okay, so how many of you know when LabVIEW FPGA was first introduced? Anybody?
LabVIEW 7?
LabVIEW FPGA. So it was back in 2004. I actually saw it on Jeff K's presentation. So 2003, 2004. So the point is, it's been around for over a decade. But developers still feel that it's like this scary, mysterious module. It's almost as if you're dabbling in the dark arts. So the code can be quite complex. But one of the benefits is that the development workflow is very, very similar to vanilla. So while we can't really do much about like the bit file compile times, there are other things that we can do to accelerate the development of LabVIEW FPGA. So in this presentation, we're going to talk about the concepts, processes, and tools that we use at Texas Instruments to automate the test of LabVIEW FPGA. So my name is Ching. I'm a software engineering manager. I'm a CLA, CTA, as well as a certified Jenkins engineer. And Jianhua, he's on my team. He's a validation engineer. He's a CLA in CTA. Okay, so we broke this session down into 4 parts. First, we're going to just kind of give you a crash course in continuous integration if you've never heard of it. Next, we're going to look at Jenkins. We're going to go through an example FPGA application of something that's simple that we can digest in a 1-hour session, which is a digital pattern generator. And then lastly, we'll talk about the test methodology we use for LabVIEW FPGA. So at the end of the session, we hope you're able to get some insight into how you can adopt this for yourself and your teams and accelerate your development. So as a central tools team at TI, we deliver a software suite to engineers worldwide to optimize their validation efforts to accelerate product launch. At the core of the automation test suite that we provide is a framework built on LabVIEW and test stand. We also have other components, such as a version control system like Perforce or Bitbucket. We also have an enterprise database. We have instrument drivers, tools and utilities, and a set of test and custom steps. So within the software suite are FPGA-related tools that we've developed for serial protocol validation. So one of the many challenges that we have with delivering the software suite in the hands of our engineers worldwide is how do we release software, quality software, at a fast pace so that we can get new features out to them as soon as possible. So in order to accomplish this, we've adopted the Agile principles. So Agile has significantly transformed the way that software has been developed and delivered. Back in 2001, we know that there's something called the Agile Manifesto. And one of the key principles of the Agile Manifesto is this principle of early continuous delivery of valuable working software at regular intervals. So it's this principle that led to continuous integration in 2006, and in 2010 continues to live. So a way to visualize this early continuous delivery of valuable work of software at regular intervals is this concept of a minimum viable product. So this concept kind of shows the difference between more the traditional software development methodology, commonly known as the waterfall model, and how it contrasts to the Agile way of doing things, where you want to do things more iteratively. So here, it allows for feedback and changes along the way, and to ensure that things that you're developing is fully functional, as well as to ensure that you're getting feedback from your customers. So what does the software development lifecycle look like for FPGA development? So I broke it down into 5 major stages: develop, unit test, build, QA, and then deploy. So for this session, we're just going to focus on the first part, the unit testing part of FPGA development, and this feedback, constant feedback. We're developing code and test, develop code, test. So the feedback that we receive from this iterative process, right, is essential to identify issues in the code, especially when we do a lot of unit testing. So in the case of the team, we want to make sure all of the members of the team's code that gets submitted is all playing nicely. So that's the definition. Continuous integration includes continuous testing. So it looks something like this. We have developers submitting code into a version control system, whether it's Git, Force, Bitbucket, Imperialware, whatever it is, and then you go and do some unit testing or some component testing. Or, you may refer to it as functional testing. So what you can do is utilize something, a continuous integration server like Jenkins, to automate this process for you. So how it typically works is when you submit code, or when a developer submits code into a version control system, that version control system will then notify Jenkins, and Jenkins will then do what you tell it to do. What, in this case, we want to go and execute some unit tests. So Jenkins is written in Java. It has a REST API, so you can call it remotely. It also has a web interface where you can configure these jobs that you want to do, whether it's builds or unit tests or what have you, these automation steps. And then you can also configure Jenkins in a master and slave configuration. So where you have a central server, which is the master. The master contains all of the job configuration, and then you have slaves, which act as kind of like workers. And so maybe you have a Windows slave that does your LabVIEW type action on type items. Maybe you have another slave that's dedicated to Visual Studio stuff. You want to do MS Build and things like that. Maybe you have a Linux slave where you're going to, maybe create some dev packages or run Gradle or something. So if you can run unit tests on a dev system, why would you want to do this with an automated system? That's a good one. We forget to run a test. So, yeah.
If you change something afterwards, you are sure you will be real good all the sense of all some changes.
So, I'm sorry, can you repeat that again?
If for your versions you something from the previous code that you already did, and it's not compatible with something else, the test will fail. And you have automated testing according to build, so to make sure that all tests are done.
Right, so
You make things that you don't need to run the test, but the test fails.
yes, so it's kind of like same idea to ensure that unit tests actually do get run all the time. Right? So on the other hand, no. So another reason why you would want to do this is to have a dedicated confined environment. Right? So how many times have you heard, well, it works on my dev system? Right? That happens. So we want to have a dedicated environment to ensure that those, because your dev systems miss. Dependencies all over the place, working on multiple projects, right? So you don't keep track of all that stuff. But with a build system, you have a dedicated place where that is done. But also in like a team environment, right? You can, when something breaks, the entire team can see what's going on. You can see trends and things, and so you can kind of collect those things and aggregate that information. So the idea is you can extend this. Right? You can extend it to do an actual bit file building, and you can also extend it to system tests or integration tests, where you actually go and deploy the bit files to physical targets and then run the integration tests. So, a little background on automation servers. Automation servers, they rely on exit codes. Right? So if you want to run something, and then you want to report that the password failed, it relies on an exit code to tell you that. The challenge with LabVIEW is it's an editor. Right? It was never designed to be like this build engine. So it doesn't give you an exit code. So James McNally, where Spin Technologies, wrote an excellent C# console application that kind of bridges that gap for you. So you call this command line interface, that then calls LabVIEW, and then within LabVIEW, you're able to then send information to standard output of that console application, and then at the end of what you're doing, then tell it to exit with a specific error. So the first block, which is the LabVIEW library, that will parse the input arguments. And then the second block is if you want to send text to the console of the console application. And lastly, you can set the exit code. So you can think of this as kind of like as I mentioned, like a proxy server. So you run this, and then the LabVIEW process becomes kind of like a child process. So this is a very simple way of executing, whether it's build or unit tests. So there are two frameworks in LabVIEW that you can actually output JUnit XML results, and those are currently the NI unit test framework. So Matt Pollitt, NI Systems Engineering, recently just released some packages that allows you to do this. So this is so you can see this is just kind of an addition to the previous code that I've shown. So at the beginning, so let me just talk about the command that's actually executed at the bottom first. So what we're going to do is launch the console application with LabVIEW-CLI. The next switch is optional, which is a kill switch that ensures that the LabVIEW child process actually dies. And then there's another switch, which is the LV-ver switch, because the command line interface will auto-detect which versions of LabVIEW you have running, and it will launch that appropriate version. And then we have this that I show you here, which is the code to actually go and execute unit test framework tests. Then you pass in the LabVIEW project file where all your unit test framework tests live, and then also then the output XML file. So the second block here is where all the magic happens. That's actually going to execute your unit test, and then from the results of the unit test, it will then output to the XML file. Similarly, with JKI VI tester, they just recently released an update to VI tester to version 2, and they also released a plugin to VI tester that allows you to output results to the XML. So similarly, we have the first block that takes in the arguments. Second block, which you need to kind of initialize the XML recording, and then you give it the LabVIEW project file where all the tests live. So the XML files are, they're not human readable. I mean, they are readable, but let's say you have hundreds of results, right? How are you going to look through the next one? So in Jenkins, you can extend the functionality to consume these XML files. So one of the plugins that you can install within Jenkins is the Jenkins JUnit XML plugin. Here, all you need to do is specify after you've executed whatever job you want to execute, you can have a post action that goes and consumes these XML reports that you generated. So here I just put star.xml. Consume all of them. Maybe you have multiple sets of unit tests that you want to provide. Then, with that same plugin, you can provide your visualization of what happened to that particular unit test run. It'll give you results like how many tests were run, how many have failed, and then you can actually go in and take a look at additional numbers like how long it would take to execute those individual tests. Okay, so before we move on to the example part of the session, I just want to give a short break to see if you have any questions on those first two parts. Hopefully that gives you an idea of how you can kick off one of these unit tests. Okay, well, if not, I'm going to pass it over to Jianhua. He's going to go over an example application, which is the digital packaging.
Hello, good afternoon, everyone. I will show you a simple example of the automated testing of a LabVIEW FPGA project. So, software testing will be complex when you do the FPGA because they have layers involved. Most of the FPGA projects that we have multiple layers, like the FPGA to Windows, or FPGA to real-time, or FPGA to real-time to Windows. So this example is a simple digital generator, pattern generator. So it will adapt the FPGA to Windows architecture, and the hardware will use a flex real and digital adapter module. So this is the architecture of this application. You can see there are two layers: the Windows PC layer and the FPGA target layer. In the host layer, there are four parallel loops. So the first loop is the UI event handler. It will capture the UI action events, and the command sender loop it will pass the UI events and send the command and the message to the FPGA through the host to target FIFO. The monitor data reader loop is for read the monitor data from FPGA, and the monitor data updater loop is for update the information to UI. Okay, so then in the FPGA layer, then we will have two parallel loops: the generate loop and the monitor loop. The generate loop will pass the command and message come from the host, and also we will set the patterns to FPGA IO lines, and also we will set the monitor enable flag when got the related command. The monitor loop is will monitor the FPGA IO lines and send the FPGA IO line states data to the host. Okay, so this is the architecture for this simple example. So here is the unit interface of this example. There are on the front panel there are several sections. The generator setting section is for set the parameters for pattern set the pattern generator. So we will select the FPGA IO lines. That means which IO lines we will set the pattern to the FPGA IO lines, and then also the states of each IO lines and how long the state will keep. So that section is set the parameters for patterns. And the other one is the monitor section. It also needed to select which IO lines we need to monitor the states and how long we will monitor the IO lines. Also other configurations for passing the monitor data and the waveform, so we are easy to view and analysis. Besides that, they also have some action buttons and the two digital waveform graphs. The digital waveform graphs is for display the generated waveform and the monitor waveform. So all the testing we will do is to ensure all the commands and the parameters are sent to the FPGA properly. So for the testing, usually the testing will have three layers, like the unit testing, component testing, and system testing. The component testing is for test the fundamental level IP, like the individual VI. The component testing is to test the compilation of the units and modules. The system testing will happen after the integration, so it will check the software work or not in the real hardware system. So each of the test level, there are multiple methods to implement. We got a recommended table from the NI website. So from that table, we will choose the execution model for FPGA VIs. So for the unit testing, we will use the choose the execution mode is the Windows PC. So the FPGA VI will run execution on the Windows context. The component testing, we will choose the simulation mode for execution mode. And then the FPGA VI will execute on the development compute with the simulation IO. The system testing, we will select the FPGA topic, so then all the FPGA VI will compile to bit file, and they will run on the real FPGA topic hardware. So this example, we will just focus on the unit test and the component test because the hardware limitation here. Okay, so here is the application. The host VIs here. We will create a unit test for all the VIs, and because the host VI it will communication with the FPGA, so they'll have some VI has the interface code there. So we could use the case instruction to bypass the interface code, and we could use the function global VI to set and get the defined testing data. So like this host to topic write method, we can use this method to bypass. For the FPGA VIs, because we decided to implement the unit test of FPGA VI on the Windows context, so we drive the copy of the FPGA VIs from the FPGA topic to the my computer, and because some of the FPGA VI will have some FPGA topic specified code, so we can use the conditional disable instruction to bypass it, and use the same function over VI to set and get the defined data. Okay, for the component testing, we will configure the FPGA target to the simulation mode. So in the FPGA target property dialog, we can go to the execution mode. We select the simulation there, and we use the custom VI for the FPGA IO. So we specify a path there, and we create the custom VI from the template, like this VI. In this custom VI, we can use the same function global VI to set the test data, so that we can get the known FPGA input and output. Okay, so this is all the test case for the unit testing and the component testing. We will use the NIWeek test framework to implement this, because NIWeek unit test framework have a lot of benefits. Like we can use the test vectors and user design test, and the test result also have a lot of statistical information. So when we create a test case there and run the test in the LabVIEW, we got the test result like this. So then we can go to a short demo to the set up the Jenkins and what it look like, the application and the test case.
Okay, so how many of you have set up Jenkins before? So if you never set up Jenkins, and you may think it's a little bit challenging to put together a Linux system or have another dedicated Windows system just to do this kind of stuff. But there's an alternative, right? And the alternative is to run a virtual machine. So traditionally with virtual machines, you still needed to set up Linux and then download, figure out how to get these packages installed on your system. How many have heard of Docker? Okay. Yeah, so you can think of Docker as kind of like a lightweight virtualization. So with Docker, you can just download these images on Docker, and you can have a fully functioning service for you to test these out before you want to deploy it to a full-scale system. Okay, so let's take a look at it. Okay, so I just have Docker running. I've actually downloaded the images for both Jenkins as well as Perforce that I'm going to use as the version control system. So here I've already pre-configured Jenkins and Perforce as well. But what I'm going to do is just kind of just start them up. Yes. So how Docker works is so on Windows 7, I have to run Docker toolkit. Right? Because in Windows 10, you can run native. So in both, what happens is you actually spin up a Linux virtual machine, which has this virtualization within it. So then you can utilize the images on top of it. Linux virtualization. So here I've spun up my Jenkins master. I'm going to spin up my Perforce server. So I'm going to launch the Perforce client. And you can see that I have a version control system running with my code that we've checked into. And then we have Jenkins running. So we'll first take a look at this job here. So when you create a Jenkins job, there's a number of different configurations. The most basic one is called freestyle. So freestyle is just, I'm going to just do some very basic things. I may check out some files from my version system, and then I'm going to execute something. And then after I execute something, I'm going to do something with that. So whether it's the output from your build, or in this case, I'm going to take those XML files and consume them so that I can display the results of the details. So here I just define the project. I'm going to go down here. I'm going to get files out of my Perforce server. And then I'm going to clean up the workspace in case there's anything residual from the previous build. And then I'm actually going to run this command. So this is the command, or very similar to the command I showed previously that will launch the command, the LabVIEW command line interface. It'll launch the wrapper to get all of the unit tests started up, and then it will finally then create an XML file. And here is that screenshot of the post-action step, where I'm going to consume the JUnit XML. So when you've actually run it, this is the test results that will show here. Similarly, with Jenkins 2, what they've done is have something called pipelines. So with pipelines, what you can do is define your Jenkins jobs by using scripting. So with pipelines, you can use a programming language called Groove, which is kind of like JavaScript, which runs in the Java virtual machine. So you can have access directly to the Java objects. So with pipelines, what you can see is you can define the various stages of what you're doing within a video. So instead of in the other method where you have all these blocks of things you want to do in this long, huge page, you can define these stages. So the first stage, we're going to clean up the workspace. Then the next stage, we're actually pull the code out of version control. Next, we're actually going to run those unit tests. And then finally, we're going to publish those JUnit XML results. So what I'm going to do is what we're going to do is describe, we're going to take a look at the FPGA code first, so you can kind of get a sense of what we're testing. And then at the end of that, we'll actually go and run this.
Okay, so we go to the project file, and the host, we can see an FPGA target there. So in the host, there have a host via NIWeek. You can see this is the one panel we just looked in the slides. And there in the background, we can see the four loops we just looked at. Okay, so we go to the FPGA NIWeek. We can see the FPGA have two parallel right there, and each of the parallels. The first one is the generator, and the second one is the mount. So each of the FPGA VI either will have a single side timing loop, and that is for us easy have a precise timing control. So this is the two main VIs. So we go to the test case. They have a unit test folder and component test folder. So in the unit test, we can see that FPGA unit test and host unit testing. So we can see that some of the test case we also create a test vectors there. We use test vector. So we can see open that test case. We can see in the test vectors item, we will see the input and output combination value is there. So this is 7 combination we will use the test cases. So go to the test case, we can configure each of the input and output, send the test vectors for them. And so this is test case, we use test vectors. So, okay, so this is the test case we create and the application code we create. So actually we also can create implement the tester in the LabVIEW here, but we have no time to do that. We will show the demo in the Jenkins automatically to test this.
I'm just going to check out all the files first. Then what I'm going to do is go to one of these files that I'm working on. this VI is a very simple VI. We're just going to do a join here. And so right now it's functional, but we're going to purposely break it. So we're going to enable this. I'm going to save it. And I'm going to then just exit. Then in the pending list, in the pending list, this is the only file that I just changed. What I'm going to do is submit that code and just say, that file was rotated. So when I've submitted that code to Perforce, actually, my local region. So how it works is, whether you're running Perforce or Git, in those version control systems, you can do post-commit actions. Right? So in Subversion, Mercurial, Git, they're known as post-commit hooks, and then Perforce are known as triggers. So once those happen, you can then have a version control system call the REST API in Jenkins to go execute this build job. So in Perforce, you can see that there's the script I've included that actually does a curl to Jenkins, and then to have Jenkins fire up this job. Then Jenkins will then go ahead and then start running this. So we'll just take a look at what's going on here. So I think because my slave is not up, it's not happening. So what we can do is just go ahead and terminate this. And so when you replay, it'll actually do what I've defined in the scripting for the pipeline. So I forgot to mention previously, along with the source code, you can have something called the Jenkins file. The Jenkins file is where those Groovy scripts live. And what you can do is actually version how you want to do your builds. So you can do that with something called a Jenkins file. And when you create a pipeline in Jenkins, it automatically understands that when you point to this repository, or it knows I should go look for this Jenkins file. When I retrieve it, I'm going to execute what is inside this file. So here is what's actually being shown inside that Jenkins file. So what we're going to do is just rerun this script. When we do that, you'll see that the LabVIEW-CLI is whatever so we've launched the LabVIEW command line interface, which spawns LabVIEW to do So it runs as kind of like a sub-process on your station. So you won't see it interact with the desktop. I've never done that, but I think it depends on how you've configured the agent to run.
So if you're running the agent through the user, so that's why it's
Yeah, it may be if you use the local system account and check a lot of the service in your desktop, and it might pop up. I've never actually tried that.
I shouldn't use this time to be looking at it.
Right, so if you actually have this on a build server, and then we'll look at it. So here, it's, you can see what the latest check-ins were. The comment that I made with this last change list. And it should be making its way through the tests. So far, it should be almost done. 2 minutes and 33 seconds. And typically, it takes 2 minutes and 7 seconds or so.
Does your unit FPGA have all of the unit tests in it? Like, is there a way to set things up so you're getting feedback in Jenkins as it's running?
So,
We use Jenkins for builds, but so it's like blind, right? Builds means it's done, like kind of like what? So, is there a way we're using the framework to get feedback on those tests?
so I think that's probably, with NIWeek test framework, that's probably a limitation of how that is. Because that's just kind of like, you tell it the project file, you say go, and it just kind of hangs in that API call until it's done. You can probably break it up. You know, instead of calling the project file, you can maybe call groups.
Folders of tests or something?
Yeah, something like that.
So at least you can know.
Yeah, what progress
So you
is.
can kick it out.
Yeah, so you can see with that commit I made, I broke that particular test. It claims it's unstable now. And then you can see that if I refresh this, you can see that the test trend it's ready. And if we take a look at the test results, you can see exactly which tests have failed. So also just recently released by LabVIEW, who develops the open source of Jenkins. They also released something called Blue Ocean, which is a different visualization of these pipelines. So here you can actually see the various stages. You can break out, it breaks out how each one of those, or I should say the output of each of those stages. And up here you can look at the tests, and it'll give you a nicer visualization of the results. Okay, so what I'm going to do is just fix it, submit it, run it again, and we'll see that hopefully we get the result.
So with the Docker installation, can you usually set that to as a service as well, so it would start up automatically with the server?
Yes, so the whole idea of Docker is you can script everything. You can script the creation of images, you can script the deployment of images, you can bake whatever you want, distribute them, to multiple servers. So you can scale them within the server. We have multiple instances running, and we have them be kind of like a pool of resources if you wanted. So it's incredibly scalable. But it's still very Linux. So Windows has started to adopt Docker natively in Windows Server 2016, I believe, and also with the latest builds of Windows 10 run Windows containers natively. And you can also, you guys know, .NET Core, and start playing around with those type of applications. So let's see, where was that piece of code that here I'm going to just re-enable this, save it, oops, and check it out. Okay, I'm going to just exit everything and revert anything that changed. So all we have is this file again. That is fixed it, submit, and we'll say fixed. Control A, T, fix it. Submit it. The force will have triggered. So you can see here, there's another build that was kicked off. We want to get a visualization, a nicer visualization in Blue Ocean. And here you can see it kind of dialing up. Let's see the progress based on previous execution times. Any questions while we wait a couple more minutes for this thing? So did you guys understand the part about taking your FPGA code and then moving it to your Windows context to text? Any thought about that? Oh, okay. Excellent. Yes. Yeah. All right, so as we wait for that to conclude, I will conclude the session by saying, hopefully, you get some insight on how you can kind of automate your FPGA testing and hook in Jenkins to put this together so that you have faster accelerated development of your FPGA. definitely in team development is definitely valuable. We have, our team is not in one location. Our team is spread out across the world. We submit files at the same time at different times of the day. We want to always be continuously moving. So in the strictest sense, everybody should be committing to master. Continuous engagement. I know a lot of people have diverged and functional branches and merge. But for us, we commit on master all the time. If we do branching, it's very short, a day or two at most. So definitely team integration of code is definitely helpful to kind of visualize, see what's going on, see your trends. Maybe one particular BI breaks a lot. Why does that break? Maybe it's a little fragile, the way that it works. And you want to kind of take a look at this.